Okay, hello everybody. Today we are going to learn one more thing about interface mass transfer in chapter 3, which is the fusion between different phases, what's happening there. The objective is to calculate the interfacial mass transfer rate in terms of local mass transfer coefficients for each phase. Well, it's two sentences, but remind you, we want to calculate. That means there should be some computation regarding the rate of mass transfer, and it should be in terms of mass transfer coefficient. But he defined it as a local mass transfer coefficient for each phase. So for two different phases, there will be different mass transfer coefficient for each phase. So having established that departure from equilibrium provides the driving force for diffusion, we can now study the rates of diffusion in terms of the driving forces. So previous lecture, I introduced you to the equilibrium into mass transfer, and we said that if it is further away from the equilibrium, then you have the driving force. If the both phases are in equilibrium, that means the driving force are zero basically. So that's that. We already explained this last time. So assumptions, many of the mass transfer operations are carried out in a steady flow fashion. Yani you don't have it as a batch, mostly you have it as continuous flow. Of the contacted phases and under circumstances such that the concentration at any position in the equipment do not change with time. So you have a kind of homogeneous concentration in the phases. So let us consider, now let's take example, let us consider absorption of soluble gas such as ammonia from a mixture with air by liquid air in a wetted wall tower. We will take this wetted wall tower, but just for simplicity, we have a column. We have this column and we have the gas and ammonia basically is coming from the bottom of the column and is going up, whereas the liquid is coming from up to down, and you have the contact between these two phases. So we have gas phase, we have liquid phase. The ammonia air mixture enter at the bottom of the tower and flow upward, while the water flow downward around inside of the pipe. So this is what's happening. You need to imagine this, that gas is moving from down to up, and the liquid is coming from up to down. It cannot be the opposite, it has to be this way. So if you have it this way, what is going to happen? The ammonia concentration in the gas mixture diminishes and it becomes lower as it flows upward. So when it goes upward with the air, the water will absorb this ammonia. So the concentration of ammonia in the air mixture will be less and it will increase in the liquid. So as it flows downward and leaves at the bottom as an aqueous ammonia solution. Assumption, under a steady state condition, the concentration at any point in the apparatus do not change with the passage of time. As this is, we already said it, that the concentration is not changing at any point. That means as a location wise, it will stay as it is. Yeah, at the top is different, at the bottom is different, but any point in between, it will be same value. It will not change with time. So consider now a situation at a particular level along the tower. Now you decide to make an experiment and you choose any elevation, any distance. And since the solute is diffusing from the gas phase into the liquid, there must be concentration gradient in the direction of mass transfer within each phase. Now we have ammonia going into the liquid. So there is a mass transfer of ammonia from the gas phase to the liquid phase. So that means there is mass transfer. That means there is concentration gradient. And for concentration gradient, we said from high concentration to low concentration. So in the air at the beginning it was high, the ammonia, then it becomes contact with the liquid, so then the ammonia moved from gas to liquid. This can be shown graphically in terms of distance through the phases, as in the figure where a section through the two phases and contact is shown. Now I'll show you, this is a very nice graph. It shows you the concentration on the y-axis against distance on the x-axis. So there is a vertical line in the middle. This vertical line is called the interface. There is gas phase on your left and liquid phase on your right. So now imagine these are two countries. If there are any two countries, what is happening between them? There is a border. So now liquid phase is a country, gas phase is a country, and the border is the interface, like that. So what's happening for the ammonia? Well, we said it is moving from gas to liquid. So, but how it is done? Look at the concentration. The concentration of ammonia in the gas is called YAG. That's in the bulk of the gas phase. Then its concentration as it comes to the border or the interface, the concentration of ammonia becomes less and less. But it is non-linear, as you can see. So it is moving in non-linear fashion from YAG to YAI. I means interface. Then, now that's the border. What is happening regarding liquid, its concentration in the liquid? It will start from XAI to the bulk, which is XAL. So the concentration, it will reduce as it moves away from the interface. So that's how the two resistance theory tells us, or two film theory is telling us. So this is how it is shown nicely, what is happening for the ammonia when it moves from gas phase to the liquid phase. The concentration of ammonia in the main body of the gas is YAG, mole fraction, and it falls to YAI at the interface. In the liquid, the concentration falls from XAI at the interface to XAL in the bulk liquid. The bulk concentration YAG and XAL are clearly not equilibrium. They cannot be equilibrium, because if they are equilibrium, we say there is no mass transfer, so it cannot be in equilibrium, since otherwise the fusion of solute would not occur. At the same time, these bulk concentration cannot be used directly with mass transfer coefficient to describe the rate of interface mass transfer, since the two concentrations are related differently to the chemical potential, which is the real driving force of mass transfer. So we cannot also combine them directly. We cannot say, oh, the concentration of the ammonia in the gas and the concentration of ammonia and liquid. These are two different things, liquid and gas. You cannot do that. You have to do something else. So how they manage to mathematically find a solution to this problem? Well, to get around this problem, Lewis and Whiteman in 1924 assumed that the only diffusional resistance are those residing in the fluid themselves. So the resistance to mass transfer, the diffusional resistance, are the ones which is in the fluids themselves. Yani you cannot have a resistance in the border, in the interface, only in the gas phase and only in the liquid, yani two resistances. There is then no resistance across the interface separating the phases, and as the results, the concentration YAI and XAI are equilibrium. There is no resistance, that means they are in equilibrium, given by the system equilibrium distribution film or curve. This concept has been called two resistance theory. So basically, you have the resistance and the fluids themselves. Notice that the concentration rise at the interface from YAI to XAI is not barrier to diffusion in the gas liquid direction. So there is no any resistance there, because if you look at the diagram, look at the diagram. you can see that XAI was a bit higher than YA, but there is no resistance here. Okay, they are in equilibrium, but there is no resistance. So they are equilibrium concentration and hence correspond to equal chemical potential in both phases at the interface. The various concentration can also be shown graphically as in the next figure, whose coordinates are those of the equilibrium distribution curve. We'll show you another diagram. If you look here, this is the diagram. Basically, it is the mole fraction and the gas, and the x-axis is the mole fraction and the liquid. You have the curve, which is equilibrium distribution curve between y and x. And then there are 2 points, point P and point M. Point P is actually, if you look, there are the coordinates of the point P is basically YAG. That means the mole fraction of A and the bulk of the gas, and XAL. That means the mole fraction of A and the liquid. So that's the point P. Point M is also you can get it. It's clearly shown to you. It is basically the values of YAI and XAI. That means the equilibrium mole fraction. And you have a line between these two, and it is straightforward. So basically, point P represents the two bulk phase concentration, and point M, the ones are at the interface. For a steady-state mass transfer, the rate at which A reaches the interface from the gas must be equal to the rate at which it diffuses to the bulk liquid, so that no accumulation or depletion of A occurs at the interface. So the rates are equal, there is no accumulation terms there. We can therefore write the flux of A in terms of mass transfer coefficient of each phase, and the concentration changes appropriate for each one of them. So from now on, we are trying to find a kind of mathematical relationship, but to do the mathematical relationship, we should do it in each phase. So let us assume at this point that we are dealing with dilute solution. We always do this assumption, and both the liquid and the gas phases. Furthermore, in both phases, substance A diffuses through non-diffusing substance level air in the gas phase and water in the liquid phase. So you have the solute, which is your ammonia, moving from one place to another one. So therefore, the development that follows will be done in terms of the K-type coefficients. The general results in terms of the F-type coefficients will be presented later. So we agreed from the beginning, from the previous chapter, we have different type of mass transfer coefficients, and we are dealing specifically for this case as K-type coefficients, small k. It is not capital K, it is a small k. So in that case, the flux NA is equal to mass transfer coefficient or the resistance multiplied by the driving force. The driving force in the gas was YAG minus YAI. In the liquid, it was XAI minus XAL. And you multiply by the mass transfer coefficient in the gas and mass transfer coefficient in the liquid. So flux is equal to K-type coefficient, KY, multiplied by driving force equal to, again, it is mass transfer coefficient in the liquid multiplied by the driving force in the liquid. If you rearrange it, basically, K minus Kx over Ky is equal to YAG minus YAI divided by XAL minus XAI. If we go back, basically, this is the slope. Slope, you can see it is minus Kx divided by Ky. So that's the slope of the diagram which was shown to you. It is providing the slope of the line PM. If the mass transfer coefficients are known, the interfacial concentration and hence the flux can be determined. either graphically by plotting the line PM on the equilibrium distribution curve, or analytically by solving the equations simultaneously. So basically what he's telling you, you have this equation, uh, how to find the values of xai and yai. You cannot do it except if you know the slope. So you have to solve these two equations actually, and by solving those two equations, you can find the concentrations in the interface. We will try to take example at one stage and to apply this kind of equation. So basically, these are the two resistance theory. There was one resistance in the gas and one resistance in the liquid, and this is how they dealt with explaining how mass transfer is happening between two phases, uh, as we have seen from this diagram. So it's important you know how this diagram is proceeding.